When you gaze upon the vast expanse of the universe with its planets, stars, and galaxies, one fundamental question clamors for an explanation. Why is there something instead of nothing? The enigma deepens when we ponder the symmetry of the laws of physics governing our universe. These laws seem to treat matter and antimatter equally, yet upon observation we find that the stars and galaxies we see are predominantly made of matter, with antimatter scarcely present. This leads us to ponder the intricate forces that created the asymmetry, giving rise to the world as we perceive it. What profound mechanisms tip the balance, granting us a universe teeming with galaxies, stars, and the mystery of our own existence? How did this unimaginably vast universe come into being? For centuries, scientists believed the universe to be eternal and unchanging, governed by the immutable laws of physics. However, in 1927, a Belgian priest and scientist named Georges Lemaitre proposed a different idea. He suggested that the universe began as a large primeval atom that exploded, giving birth to the smaller atoms we see today. Although Lemaitre's idea initially received little attention, in 1929, astronomer Edwin Hubble discovered that the universe is not static but is, in fact, expanding. This revelation led some scientists to speculate that if we were to rewind the universe's history, it would contract back to a tiny, dense point. This concept was mockingly dubbed the Big Bang Theory by astronomer Fred Hoyle, a name later embraced by its proponents. Undeterred by skepticism, scientists Ralph Alpher, George Gamow, and Robert Herman predicted that if the Big Bang had occurred, a faint afterglow should permeate the universe. In the mid-1960s, astronomers Arno Penzias and Robert Wilson stumbled upon this cosmic microwave background radiation, the echo of the Big Bang, while attempting to tune into microwave signals from the Milky Way. If the Big Bang theory holds true, how did it lead to the formation of planets, stars, and galaxies? Through meticulous calculations and observations from telescopes on Earth and probes in space, our best explanation emerges. Approximately 13.8 billion years ago, all the matter in the universe erupted from a single infinitesimal point of singularity in a violent explosion. This expansion occurred at an astonishing rate, doubling in size every 10 to the power of -34 seconds, creating space as it rapidly inflated. Within a fraction of a second, gravity and other fundamental forces formed, and energy transformed into particles of matter and antimatter, most of which annihilated each other. Fortunately, some matter survived, giving rise to protons and neutrons within the first second. Shortly thereafter, these particles began to fuse, forming hydrogen and helium nuclei. Around 300,000 years later, atoms began to form as nuclei captured electrons, filling the universe with clouds of hydrogen and helium gas. Approximately 380,000 years after the initial explosion, the universe left behind a residual glow, the cosmic microwave background radiation that Penzias and Wilson serendipitously detected. Within this radiation were minuscule fluctuations in matter, stretched to cosmic scales during inflation, which ultimately served as the seeds for the formation of galaxies and galactic clusters as we know them today. Today, when we survey the vastness of the universe, our comprehensive observations, despite inherent uncertainties, consistently point to a coherent narrative. Our universe comprises matter and adheres to the unchanging laws of physics across all space and time. It operates under the umbrella of general relativity, expanding, cooling, and gravitating with its dynamics influenced by dark energy and dark matter, complemented by normal matter, neutrinos, and radiation. Within this cosmos we find a tapestry of galaxies, stars, planets, heavy elements, and even intelligent life at least in one corner. These cosmic structures did not exist from the outset but emerged through a process of cosmic evolution. A remarkable feat of scientific deduction achieved in the 20th century, scientists reconstructed the timeline detailing how our universe transitioned from a largely uniform state, devoid of intricate structures and primarily composed of hydrogen and helium, to the diverse and complex universe we behold today. If we trace backward from our current vantage point, we confront the question, how did each individual structure or component come into being? Iteratively, we delve into the origins of each constituent, probing deeper until we encounter the limit of our understanding. Yet even amidst this uncertainty, we contemplate the genesis of existence itself. Could all that we see arise from nothing? Life as we know it stems from the minuscule particles composing the fabric of our reality. These particles assemble into complex molecules, the building blocks of life, fashioned from even smaller entities known as atoms. However, atoms did not materialize ex nihilo at the universe's inception. Rather, they underwent a protracted process of formation. This process unfolds within the cosmic drama of stellar life cycles. Stars are born, live out their celestial lives, and ultimately perish, catalyzing the creation of new materials through cataclysmic processes. These materials in turn fuel the birth of successive generations of stars, perpetuating the cosmic cycle. This intricate interplay sustains the conditions necessary for the emergence of planets and the intricate chemistry essential for life. For the universe to manifest in its present form, several pivotal events had to occur. Gravity orchestrated the aggregation of stellar and galactic ensembles, necessitating an initial mass that gravitational forces could sculpt into larger structures. Dark matter played a crucial role in preventing the dispersal of matter during the nascent stages of cosmic formation. Moreover, a delicate equilibrium of various forms of matter and radiation was essential for the generation of cosmic relics like the cosmic microwave background radiation and the elemental constituents of galaxies. Central to this narrative is the puzzle of matter-antimatter asymmetry. In the primordial crucible of the early universe, matter and antimatter should have coexisted in equal measure, yet our cosmos predominantly comprises matter. Various hypotheses attempt to elucidate this disparity, involving scenarios where standard physical laws undergo temporary aberration, favoring conditions conducive to matter generation. Prominent among these is the concept of CP violation, interactions within the framework of the standard model of particle physics. In contemplating the origins of our universe, we confront a profound mystery. Did the universe indeed spring forth from nothingness? While uncertainties persist, our ongoing quest for understanding continues to unravel the intricate tapestry of cosmic evolution, probing the depths of existence itself. Dark matter, despite its elusive nature, is crucial to our understanding of the cosmos. While it cannot be composed of the particles described in the standard model of physics, various theories speculate on its origins. It could have arisen during the early stages of the universe's hot phase, persisting through subsequent cosmic epochs. Alternatively, it might have materialized during phase transitions as the universe expanded and cooled. Other hypotheses propose its existence as a novel type of neutrino or as a consequence of gravity giving rise to exceptionally heavy particles. The question then arises, why does dark matter exist today when the early universe seemed to function without it? The genesis of dark matter necessitates significant energy, prompting inquiry into its source. One intriguing possibility arises from cosmic inflation, our leading theory regarding the universe's pre-Big Bang origins. Cosmic inflation posits that before the hot Big Bang, the universe underwent a phase of rapid expansion, driven by an incredibly high energy density inherent to space itself. When inflation ceased, this energy precipitated the formation of matter, antimatter, and radiation, setting the stage for the subsequent evolution of the cosmos. Notably, inflation predicts specific patterns of density variations that align with observations, offering compelling support for its validity. However, while cosmic inflation provides a framework for understanding the universe's birth, it invites philosophical contemplation. Can we truly comprehend a state devoid of space, time, and the laws of physics? From a philosophical standpoint, we might conceive of nothingness as the absence of these fundamental elements, yet from a scientific perspective, defining nothingness becomes a complex endeavor. Scientifically, we can define nothing in various ways, as a time when something didn't exist, an empty spacetime with minimal energy, or the absence of the universe and its governing laws. While certain definitions might suggest the emergence of the universe from nothingness, others pose challenges. The notion of true nothingness, devoid of spacetime and physical laws, defies conventional understanding in the realm of physics. Grappling with the emergence of spacetime from non-existence raises profound questions. How can space and time arise from a state lacking any definition of location or duration? The enigma deepens when we consider the origin of the laws governing the universe. Without a clear framework describing existence beyond our universe, the concept of absolute nothingness remains elusive. Ultimately, while scientific theories provide insights into the universe's origins, they also underscore the limitations of our understanding. The quest to unravel the mysteries of existence continues, pushing the boundaries of human knowledge and perception. Quantum theory opens up fascinating possibilities regarding the origins of both fields and particles, challenging conventional notions of eternity in spacetime and physical laws. While certain assertions may suggest the emergence of the universe from a state of nothingness, the certainty surrounding our cosmic origins diminishes when we transcend physical constraints. Many scientists entertain the notion that the universe might have arisen from nothing, rooted in quantum theory. This idea revolves around the concept that quantum fluctuations could spontaneously generate a universe ex nihilo. However, lacking mathematical substantiation, this idea remains speculative. Until recent breakthroughs, Don N. Page and his team from the Wuhan Institute of Physics and Mathematics made significant strides by offering the first mathematical proof that the Big Bang could stem from quantum fluctuations. Central to their breakthrough are the Wheeler-DeWitt equation and Heisenberg's uncertainty principle. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, integrates quantum mechanics and general relativity, albeit without a consideration of time. Meanwhile, Heisenberg's uncertainty principle elucidates the transient nature of particles in the vacuum, wherein particles momentarily emerge from and vanish into nothingness due to random quantum fluctuations. Combining these principles, he and his team demonstrated that a tiny true vacuum bubble could rapidly expand, potentially leading to a Big Bang scenario. This new equation also suggests a connection between dark energy and the quantum potential, a concept derived from pilot wave theory, a lesser-known interpretation of quantum mechanics. The ekpyrotic universe theory posits an intriguing alternative to the conventional Big Bang model. In this hypothesis, our universe emerges from the collision of two higher-dimensional branes, akin to cosmic sheets within a larger unseen reality. This collision catalyzes the release of energy and matter, igniting the expansion and evolution of our observable universe. These concepts challenge our understanding of cosmic origins, inviting us to explore new avenues of inquiry. While still speculative, these theories offer tantalizing glimpses into the fundamental nature of reality, pushing the boundaries of scientific exploration and imagination. The ekpyrotic universe theory presents a captivating departure from the prevalent inflationary model of the universe's genesis. While inflation posits a rapid expansion fueled by a mysterious field, the ekpyrotic scenario suggests a dynamic interplay between higher-dimensional branes. This concept not only reshapes our understanding of the universe's origin but also introduces the notion of cyclical patterns. According to the ekpyrotic universe theory, the collision that birthed our universe may not have been a singular occurrence but rather part of an ongoing series of collisions and expansions. Each cycle could potentially spawn a new universe, suggesting a perpetually evolving cosmic landscape. Speculations abound regarding the nature of our universe within this framework. It could be the result of a grand cosmic experiment conducted by an advanced civilization in a higher dimension, designed to study the emergence of life and fundamental forces. Alternatively, our reality might be a mesmerizing projection emanating from a higher dimensional realm, hinting at the possibility of a holographic existence. Some even entertain the idea of the universe as a self-aware entity, undergoing a universal journey of self-discovery through galaxies, stars, and living beings. As we grapple with these profound concepts, it's essential to acknowledge our current limitations in understanding the universe fully. While the Big Bang remains a pivotal event in cosmic history, it may not signify the absolute beginning of all existence. Revisiting the early stages of cosmic evolution reveals a universe ripe with opportunities for life to emerge, driven by the enduring principles and materials that govern the cosmos. Despite the role of randomness in shaping our universe, the emergence of life underscores the remarkable potential inherent in the cosmic fabric. It is now our responsibility to embrace and cherish this opportunity for existence, striving to unlock the mysteries of the cosmos and enhancing our place within it.